This is MAE 4243, Aerospace Propulsion, and this is the fifth lecture in the quote turbo machinery series. We're going to continue our discussion on compressor and compressor aerodynamics today. So we'll be looking at a series of slides now, and what I want to emphasize today is we talked about the trend of compressors going from high aspect ratio to low aspect ratio, from low solidity to high solidity. And we never really, I'm recording right now. You need something? Sorry about that interruption. So we kind of just stated that as a fact, and you know, there is a real engineering reason why that has occurred. And so what was recognized was that flow through an axial flow compressor, the passages the flow flows through are nothing more than, you know, you're diffusing the flow. You're raising the pressure and you're slowing the flow down, and people started thinking of ways to give more stall margin, okay, at the same time have increased pressure ratio without actually stalling it. So something called the stall margin correlation was developed, and it's based on an analogy with 2D diffusers, something we talked about when we talked about subsonic inlet designs, where stall is due primarily to the end walls, and end walls in an annular compressor is the area near the casing in the hub deteriorating to the point where it separates, and so the idea is to design those passages kind of the way you would think about designing a 2D diffuser. It's not exact, obviously. So the idea is to correlate peak pressure rise data with cascade geometric parameters, things like chord and the spacing, okay? So this correlation is something, you know, was developed, accounts for tip clearance, Reynolds number, velocity diagram, variation, solidity, camber, aspect ratio, spacing. It does not consider anything about the stability of this. So any kind of transient analysis is not incorporated in this stall margin correlation. So if you recall, when we talked about diffusers, you could look at a diffuser, a subsonic diffuser, in terms of different flow regimes. So let me see if I can get a pointer here. I think the laser pointer was nice. So you have different flow regimes that could be possible. In the upper left-hand, number one here, you have nice attached uniform flow through the diffuser, so nothing is separated. Station 2 here could be a where separation just occurs, but it's kind of intermittent. It could happen on one or both sides, but it can move back and forth. So this is a transient stall condition. 3 is when you get a it's not transient. It's actually a steady stall from one or both one side of the diffuser. So the angle here is high enough to where the flow will separate, create a separation bubble that's fairly fixed and it's a stable separation point within a diffuser. And then, of course, if you have either too high a speed or too rapid a divergence of your diffuser angle, you get a full separation on both sides of the diffuser, and this is almost like having jet flow with some bounding surfaces. So these are the possible flow regimes in a subsonic diffuser. What we want to try to design to is, of course, one where we have attached, relatively uniform flow through the diffuser. There's been lots of work done over the years on diffusers, and back in the inlet, this is something close to, you may have seen a different plot that was close to this. There's one in your book that doesn't have actual numbers on it, but here is a plot of the divergence angle, and this is the included angle of the diffuser. okay, and this is for a 2D diffuser, versus a parameter that could be considered something like the length of the diffuser, in this case n, divided by the inlet height of the diffuser. Okay, so this is sort of like an aspect ratio, if you will, of the 2D diffuser versus the included divergence angle. And so this line, this solid line here, A to A here, is the line of the very first stall. Okay, so if you're, say, at an N over W or aspect ratio of your diffuser of 10, and you have an included divergence angle of 20, you're going to be most likely stalling. Okay, you will be stalling based on a lot of empirical data. If you're below this line, you've got no appreciable stall, or things are attached and good. So you want to be in this region down here. All these other lines here just signify when you enter those other different flow regimes. The jet flow, as I mentioned, is way up here. So if you have, this type of aspect ratio and you're at 60 degrees, you essentially have that fully separated on both sides, something that they call jet flow. So this data for 2D diffusers was, been around for a relatively long time before they started trying to correlate this with flow through an axial flow compressor. So how does this analogy work? Well, if you look at a passage through the compressor, two blades sitting in tandem, if you consider the inlet flow area W1, and then the length N would be equivalent to the length of the passage, then you consider that to be your diffusing area. And then, of course, we defined earlier what spacing was, which is the distance between the leading edge of the preceding and the blade next to it. And so you can develop these correlations, just like you would with a diffuser, with these turbo machinery blades. Now, you can build these rows of blades, and if they're not rotating, they're fixed. We call those cascades, and they can mimic rotating flows, but you have to make a correction for that, the fact that they're not actually rotating. But you can still use that as a test device to help you design. So here's kind of the guts of this stall margin data correlation. So you have some measure of the effective pressurized coefficient. Okay, so think of this as just, okay, at what point do I stall? What's the pressure ratio at which the passage begins to stall versus this diffusion length parameter, or L over G2. I think in the next slide we define that. But it has to do with this aspect ratio. And you can get a bunch of data points out there, and you can kind of see where they fall. And there was this kind of limiting line here that if you kind of stayed below this line, maybe at or below this line here, you're going to be in an area where you don't have to worry about, or not worry, but it's going to be less likely to stall. Okay? But it's based on those airfoil parameters. So to increase the maximum stalling pressure ratio, we want to increase this L over G2. So if I go back here, if I want to get higher pressure ratios without stalling, I need to make this parameter L over G2 larger. And this should make intuitive sense. I'm just stretching out the length of the diffuser. And if I do that, I'm able to get this delay the stall that much longer, right? It's just a function of the geometry. In our analogy then, the length is kind of proportional to the chord of the blade. And the solidity is proportional to the chord, and the aspect ratio is proportional to 1 over the chord. So hence, to increase the maximum stalling pressure ratio, you want to move to higher solidity and lower aspect ratio. Okay, so just so we're clear here, if you look at the geometric parameters of this turbomachinery flow passage here, we want to increase L for a given W, or width coming in, to get higher stalling pressure ratios. be able to get higher pressure ratios before I stall. Well, the implication of that is that I'm going to go to higher solidities and lower aspect ratio blades. And so when you see this trend over the last 40 years, it's the recognition of that fact. And indeed, this was this stall margin correlation became a design practice, and that's why the GE90, which was based on the E cubed, had a pressure ratio of 23 in just 10 stages, versus say the J79 compressor, which had pressure ratio of like 13, but it took 17 stages. And if you look at the blading, if you go back and look at the blading, you will see very evidently that you have the differences in solidity and aspect ratio between those two. So if we move further and talk about loss sources, we want to be able to predict loss sources in axial flow compressors. We go back to our picture of the complex flow field. It's possible to have shocks. You have secondary flows, and here again we define secondary flows as flows that are in a direction other than the through flow velocity or the axial velocity through the turbo machinery passage. So flows that move in the circumferential direction, in the radial direction, that get wrapped up in the tip vortice or any of the wakes, that's all considered secondary flows. Okay, and they're losses typically, or they're due to losses. So what we want is an efficient model to predict the maximum efficiency of a potential axial flow compressor, and what they did was consider profile losses, leading edge bluntness, passing shock losses, boundary layer losses, tip clearance losses, and part span shroud losses. We'll talk about what a part span shroud is, and what that is to a fan or even to some compressors, and it has to do with structural integrity, but it also introduces aerodynamic losses. Okay, so the blade profile losses are just like you would consider for a fixed wing profile loss. When we talk about end wall and tip clearance losses, we recognize the fact that you have to have some gap between the rotating blade and the end wall, and as that scrubs past, you're going to have high pressure air leak over to the low pressure side and create a tip vortice, and that creates a loss. So how big that clearance is going to be a key loss contribution. If you're moving supersonically, like at the top edges of either fans or some compressor blades, you can be moving the relative velocity, W, could be supersonic. Hence, you'll have shocks and you'll have shock losses. The part span shroud is a little piece that's put in very, very or large fan blades when they were made out of pure metal and steel early on. They needed to have structural rigidity added to it by these little shrouds that actually will go and almost touch or physically touch the blade next to it, and that's to help dampen some of the vibratory problems that might occur in these large blades. Well, these presence of these things that sit in between, they actually block part of the flow through the flow passage. They create loss, and so there's a loss due to what's called the part span shroud. What's not considered are any off-design losses, any losses due to just poor hardware quality, or just bad aerodynamics. So the model is semi-empirical, and it uses a theory, which just means it uses theory and experimental correlations together. Here's another way of indicating where some of the high loss regions are in a multi-stage core compressor: the end wall boundary layers, the separations, the secondary flows through the turbo machinery. These one-dimensional simple loss models, semi-empirical, are really pretty good. If you look at this is the calculated efficiency versus what was actually measured, and I believe this is a plus or minus 1% line on these dash lines. So, designing compressors that axial flow compressors that are derivative. In other words, you're not making too big of changes from one design to the next. Can lead to some very accurate predictive methods of what the losses to be expected on any new compressor is. So the design process that's been used for many, many years, and it still is a quasi three-dimensional system. So think of the axial flow compressor geometry in cylindrical coordinates, right? If you look at it in the RZ plane, right, you're looking at this side flow path view. If you look at it in the theta R plane, we're looking at flow in the side-to-side or circumferential direction. And of course, if we look at in the Z theta plane, if we actually cut across here, we'll see a flow passage like this where you have flow between two airfoils. And so you can analyze the flow in one of these planes. In fact, you normally start in the RZ plane, and you compute the fluid properties in the velocity triangle data that we talked about before in this plane. And then you feed that data into this plane, the theta R plane, and then feed it into the Z theta plane, and then you iterate on this, okay? And so you iterate this until all the flow stream surfaces converge, and you have a converged solution of flow through this turbo machinery. And you can add things to it, like that loss model, being able to predict what these secondary flows are. There's models that go into this. And so this is a two-dimensional calculation, this is a two-dimensional, and this is a two-dimensional. They can run very, very fast, and the iterations can take a very, very short time. And so you get a 3D picture, but you're doing little, a quasi 3D in each, or a two-dimensional calculation actually in each phase, okay? And you iterate this, and this is a very effective way. So here's an example of gridding up a cascade analysis. Here's looking at it in 3 dimensions, where you have to understand that when we assume that the radius is the same between the leading and the trailing edge, that's not necessarily true, and you can account for that this stream surface is actually going to be distorted somewhat as it goes from inlet to the exit station. Designing the airfoils at a particular radius is done the way that you would look at tailoring a 2D, like a fixed wing aircraft. But there's differences because of the proximity of the adjacent blades. But essentially, you can tailor the surface velocity and the pressure on the suction side and the pressure side to give you the properties and that you're looking for. If the incidence is too low, if you have, say, a negative angle of attack, you'll get pressure distributions that look like this. If you have incidence too high, where you're close to stall, you'll have pressure distributions that look similar to this. This is what a normal incidence within a range where flow is attached would look like. So you have things like the leading edge loading. Okay, these are terms that designers use. You have the peak suction region, and then you have the diffusion region of your upper surface of the airfoil that diffuses back towards the trailing edge. And of course, this is the pressure side, and you have to enforce the cutting condition at the trailing edge for these calculations. So some of the things that designers do to get that last 3 or 4% of efficiency are to custom tailor designs. As I said early on, compressor airfoil design was very, very simple. They literally used circular arcs for the upper and lower surfaces and made blades that look like that. Now with both advanced computer techniques, including 3D CFD, you're really able to tailor the loading that occurs across the airfoil that make up the compressor, right? So you can unload the trailing edge, load up the leading edge, and move the max thickness around to where you can control these things much finer, okay? And so you can see what the Invisid design might look like, and then the test. And so even using Invisid flow codes, you can get pretty good predictions of what the compressor aerodynamic loads are on each airfoil. Remember, those loads are going to ultimately determine the how much work is being put into the flow. Here's an example of looking at a pressure coefficient in the y direction here. This is efficiency on the left-hand side, and this is the flow coefficient. And the flow coefficient is defined as the axial velocity divided by the wheel speed. So this is CZ over U, okay? And that's kind of a measure of mass flow. So that's the indication. So this is, CZ over U, or some measure of mass flow along the x direction, and this is the pressure coefficient that you get when you as you change that. Okay, so let's look at the baseline is the dashed line. So as I described before, how you make a compressor map, this is for one stage, say, you would control the power into the rotor with some measured electric motor. So this is you're controlling the power into the compressor stage, and you have a throttle that governs the mass flow through the machine. So you fix an RPM. In this case, for this baseline design, you fix the RPM, and you slowly close the throttle. You close the back area that's flowing through the machine, and you measure what the pressure rise is. And as you continue to close, you move along this line, and so this is a constant speed line. At some point, it'll stall, and that's what this point is here. So think back to that compressor map I drew last time, and this is one of those constant speed lines, okay? Because we're only talking about one stage here, okay? Now, this curve here goes with the pressure coefficient line on the left here. On the right, the efficiency is this dashed line, and this goes to the right-hand side here. By doing a tailored design, so I've gone in and I've changed the aerodynamics of the airfoil, okay, I get this new line here for this rotor 2, which happens to be a custom tailored rotor. And you can see I've increased the pressure coefficient before it's over the whole range, okay? So I'm doing a much better job at compressing the air with this airfoil design, and I'm getting much larger efficiency. And you say much larger, 0.8 percentage points. That's a lot, okay? And it may not seem like a lot to you, but this translates into lower SFC, okay? When you bring this across all of the rows in your compressor, this is just one row. So this is an example of how, by custom tailoring the aerodynamics, okay, you can get better performance, both in efficiency and pressure rise. And this just shows you the different areas of the blade that you can affect, the diffusion, the turbulent diffusion, and the laminar flow that it can promote. So these are just different items that you can. So by tailoring the boundary layers, by tailoring the shapes, you can see again that you can get increased performance, both in pressure rise and in efficiency. secondary flows that are due to boundary layer moment. Remember, the flow near the wall is less momentum. In this particular picture here, the flow is coming out of the page. So the flow near the hard walls is going to have less momentum. It's going to be less velocity, and they're going to be subject to these different pressures than the flow, say, in the middle. But it does create these rotating flows near the walls, and this is something that has to be accounted for, but also is a loss. The fact that these exist, if you assume that they didn't exist, in your predictions, you'd be pretty far off. For instance, the dashed line here, this is the hub or the bottom of the blade, and this is the top of the blade, the tip. Okay, so this is a percent of the span. And this is, in this case, it's the measurement of stagnation temperature. So if you didn't assume that those secondary flows existed and you went through and you made your calculations, you would predict a span-wise distribution of temperature. I'm recording. Right. Sorry for that second interruption. So you get this fairly significant difference in stagnation temperature from near the tip and near the hub. If you incorporate the secondary flows, the fact that the flows will move from high pressure to low pressure side, and some of the as it moves through the turbo machinery, it actually mixes the flow more. Makes sense, and so the temperatures won't deviate that much at the tip and the hub, and that's what this solid line is. The symbols are actual test data, so this correlation that actually predicts the secondary flow model is able to capture what's really going on much better. Down here you have the absolute air angle. So think about alpha, right? Alpha, the absolute air angle. That can change as a function of span, okay? And again, you see here in the middle, it doesn't do too bad of a job of predicting, but if you don't assume the secondary flows, you can be pretty far off near the tips and the hub, okay? In fact, down here at the hub, you're predicting a absolute air angle of like 26 degrees when it's closer to 35 or 40 degrees. It makes a big difference, okay? And you have to appreciate this, and I know it's hard for you to appreciate. This is just a 2D and semi-empirical model, and these were developed in the late 60s, early 1970s, before you had 3D CFD, right? So these were incorporated into those two-dimensional and quasi 3D models. They were very, very successful at coming up with a rapid way to predict what these air angles and thermodynamic properties are at the hub and the tip. Okay, so that's a very, this was a breakthrough of sorts to be able to do this fast. Okay. This is CFD results, and it just kind of hammers home the point of when you have increased loading, you're going to have increased secondary flows. So in this case, this is the, you got to look at flow coming out of the page, and this is the suction side of one blade and the pressure side of the adjacent blade. Flows coming out of the page. What you see are the velocity vectors, okay, in the theta r plane, okay? You don't see the velocity vectors coming out of the page. And so if you have a highly loaded compressor, that means you have a lot of lift going on. If you have a lot of lift going on, you have a big difference between the pressure and the suction side. Makes sense, right? So at the design point, you have these types of secondary flows. In other words, the magnitude of the flows in the end walls, along the span. You can see this, and on the right is when you have an increased loading. So we have a engine condition that has a lot of work that's being put into the flow, Okay, it's off design, but there's a lot of work going on, and so the secondary flows are increased dramatically, and you can see that in the CFD, and obviously this is measured as well in terms of we know that this is supposed to happen and we can predict it. So you can see very clearly that when you have high velocities or high loadings, I should say, it increases the amount of secondary flows that you see. These are the important references where you can find all this. You know, the recognition of secondary flows goes all the way back to when they started building axial compressors. These are some really good papers along those lines. I would say the second one, and this one down here by Whistler, do a very, very good job of explaining. And in fact, this last one here is probably the best in terms of giving you a good understanding of what's involved with compressor aerodynamics in general. As you might imagine, that if you design blades with this type of secondary flows, it means that you're, especially near your the casing, near the tip, and near the hub, that it's going to want you to put air angles in kind of a weird way relative to a uniform twist, if you would. So when they realize that that would be better aerodynamically, the aerodynamicists try to convince the guys who are building the manufacturers to if you could twist these air angles or the blade angles, which lead to the air angles near the tip and the hub, you'll get much better performance. And indeed, they've been able to do that. And so they call these end-bend airfoils, where accounting for these secondary flows, you get some very unique shapes near the hub and the tip. To give you an idea of how much performance increase you get on the order of a 0.5 percentage point of efficiency. Again, might not seem like a lot, but when you run the numbers, getting fractions better in SFC over the life of something of these machines makes a big difference. So this gives you an idea of what kind of increase you get in stalling pressure rise and in efficiency by having the end bend stators. So this is the worth of why you would go to the extent of building these ways. Here's secondary flows due from leakage. Has to do a lot with clearance. So if you're able to decrease the allowable clearance, okay, this could make a huge effect. In fact, this is bigger than the other loss we just showed, that if you're able to hold tighter clearances between the rotating tip and the casing, you can get significant increases in efficiency. That tip vortice that you see is an extremely high loss content. So that's something that's been demonstrated, and finding ways to reduce that tip loss is something that's been looked at for a while. Here's another way of showing you if you can increase the effective increased tip clearance on performance penalty. Again, it's a big deal. So people start looking at different ways of handling the tip. So all these different shapes, the squealer tip, the knife edge, the groove, the winglets, all of these things were tried to reduce the amount of loss from flow coming from the pressure to the suction side as it rotated around. It essentially comes down to trying to reduce the discharge coefficient of the flow through this gap. This is just some results from 3D Invisit measurements. This is a picture from a long time ago, so this has improved a lot. But we have the ability now to look at multiple stages, full three-dimensional, Reynolds averaged 3D CFD, okay, through so that complex flow field can be modeled pretty decently now with modern computers. And so now you can start to look at really how the flow is moving, and has even a bigger impact in turbines, as we'll talk about later, regarding where you put cooling flow in. Once you know where these secondary flows and these are going through the turbo machinery passages, the better you can cool the turbine blade. When you talk about airfoils that are going to be in supersonic flow, then we go and pull information that we know about airfoils and supercritical airfoils. We can look at different airfoils that have a better way of handling that shock system. Okay, you want to do the same kind of things you do with fixed wings. You want to delay the compressibility. This is Mach number versus a loss coefficient. So if you can control that diffusion, you can extend the Mach number before the drag increases rapidly. Okay. Talked about the part span shroud. This is the E-Cube fan blade. So this is circa 1978, 79. But what's a good, it's a good indication of the different types of flow fields that you can have along a fan blade. You certainly have subsonic flow at the lower parts. It becomes transonic here. It becomes supersonic here. Okay. Again, we're talking about the relative airflow, W. Okay. So the W flow vector component can go anywhere from 0.7 to Mach 1.4 from the hub to the tip. Okay. Now, because of that, and because of the relative velocity will change, because U is going to change from this radius to that radius, that's going to change the angle of incidence, and that's why most of, obviously, fans and compressor blades and turbine blades will have different angles of incidence, geometric angles. Okay, the so-called stack is going to be different, and the thickness is going to be different. So over on the right, see if you can see how this is pictured. So think of flow coming from top to bottom, okay? And near the hub, you've got this type of airfoil shape, which is got a fairly large thickness. Again, there's structural reasons why you might want to do this. But the incidence angle is going to be in a different, the angle of attack or relative to the flow is going to be much different because of the relative velocity being dependent upon the wheel speed U, which is omega times R. R is real low here, so U is going to be low, lower than the tip, which means that the angle is going to be different. Okay, somewhere near the midspan, okay, you have this middle airfoil shape here. Notice that it's much thinner. Okay, then its max thickness is much different than it is at the hub. One of the main reasons are because you're moving much faster. Here you're moving basically sonic and transonic. Right? I want to have as minimal area as possible into the flow. And then, of course, near the tip where you're definitely supersonic, you can see a different, certainly different stagger angle, and you have a very thin, very small max thickness airfoil. Okay, so this fan blade starts out with a big fat thickness at the hub. As it moves higher to the tip, it changes its stagger angle dramatically and also gets much thinner. And so this you can imagine interpolating what this looks like going from the hub to the tip and how it changes in thickness and angle. Okay, this is just the fan blade. So those fan blades see a radically different flow field just along its span. Okay, so you need to appreciate that. Near the tip, where you have the very high Mach numbers, right, you are now designing this passage to minimize the amount of shock losses. You're going to have shocks. They're going to impinge on boundary layers. And your goal is to minimize this like you were minimizing the shocks in a supersonic inlet. So a lot of care goes into this passage design. And by the way, just as a side note, these shock waves, when they rotate really fast, when we have supersonic flow at the tips of fans and they produce these shock waves, that produces a very characteristic sound. In fact, a lot of the modern fans have swept leading edges for the same reasons why you have a sweep on leading edges of supersonic fixed-wing aircraft. It's to delay this compressibility. It's to make these shocks weaker. Early on, they didn't do that as much. In fact, because they couldn't manufacture the curvature that they can now with some fancy composites, some of the early large turbofans, because they had large diameters, had Mach numbers that were like 1.4. Those shock waves spinning around at like 15,000 RPM, and then having blades slap into those, the ones that are just adjacent to the blade generating the shock, would cause a noise that was akin to a buzzsaw. And so it's called buzzsaw noise. And if you listen to the old C5s, which were used, that had the older engines on it before they've changed them out, they had a very distinct noise at takeoff. And indeed, a lot of turbofans at takeoff have that characteristic noise, and it's due to the fact that these shock waves are being cut by the blade that's coming in its path. And so if you can anything you do to minimize that also has the benefit of reducing aircraft noise. Here's some CFD solutions of different. This is below peak efficiency. This is near peak efficiency. So you can see the difference in the strength of the shocks and where they're located. And this is just a picture of some bleed ports. I don't think I need to go into that. All right, so that's what I want to cover for this lecture. What we'll do, I'll be giving some homework out in terms of turbomachinery, aero, and we'll start talking about turbines in the next lecture. So this is the end of Lecture 5 of the turbomachinery series.